two numbers describe the same universe, and they refuse to agree. One says space is stretching at about 73.5 kilometers per second per megaparsec. The other insists it should be closer to 67. For years, astronomers assumed sharper instruments would quietly erase the gap. Instead, they did the opposite. The Hubble Space Telescope patiently built the case. The James Webb Space Telescope was then sent to break it, hunting for a hidden flaw that might explain the whole thing away. And in 2026, a sweeping new analysis pulled more than a dozen independent measurements into a single framework, and the disagreement only grew louder. Something between the universe's first light and the night sky above you does not add up. Tonight, we find out what is. If you find yourself hooked by the biggest unanswered questions in science, it would mean a lot if you tapped like and subscribed. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. Somewhere inside the ledger that describes the entire cosmos, two numbers sit next to each other, and they were never meant to disagree. One of them is about 73.5. The other is about 67. They are answers to the exact same question: how fast is the universe growing right now? And for a long time, most astronomers assumed that the small gap between them was a temporary embarrassment, the kind of thing that sharper instruments and more careful work would quietly smooth away. That assumption has aged badly. The gap did not close, it hardened, and by the year 2026, it had become one of the most stubborn problems in all of physical science. Serious enough that the people who study the birth and the fate of the universe now discuss it in lowered voices. That problem has a name. Astronomers call it the Hubble Tension. But before the name can mean anything, you have to understand what these two numbers are actually counting. Because nearly everything in this story hinges on a single strange fact. The galaxies are not simply drifting apart through space like debris scattering across a still room. Space itself is stretching, and it is carrying the galaxies along for the ride. Picture a loaf of raisin bread rising in a warm oven. The raisins do not crawl through the dough under their own power. The dough between them swells, and as it swells, every raisin drifts away from every other raisin. A raisin near you moves off slowly. A raisin on the far side of the loaf, with far more expanding dough piled up between you and it, races away much faster. No raisin is special. No raisin sits at the center. From the point of view of any single raisin, all the others are fleeing, and the distant ones flee fastest. That is the universe. You are one raisin. Every galaxy you can see is another. And the dough is space itself, quietly inflating in every direction at once. This is the piece that trips up almost everyone the first time they meet it. When astronomers say a distant galaxy is moving away from us at thousands of kilometers per second, they do not mean it is flying through the void like a thrown stone. They mean the space between here and there is lengthening. So light that left that galaxy long ago has been stretched during its journey. Its waves pulled toward the red end of the spectrum. We call that stretching redshift. And it is the fingerprint of an expanding universe printed directly onto starlight. The farther away a galaxy sits, the more expanding space lies between us, and so the faster it appears to recede. Distance and speed rise together, hand in hand, all the way out to the edge of what we can see. The number that ties those two things together, how much extra speed you gain for each extra step of distance, is the Hubble constant. It is, in a sense, the pulse of the cosmos, the single figure that tells you how vigorously space is unrolling today. And the units it comes wrapped in sound forbidding at first, so let us take them apart slowly, because once you feel what they mean, the whole mystery clicks into focus. The Hubble constant is measured in kilometers per second per megaparsec. A megaparsec is simply an enormous unit of distance, a little over 3 million light years, the sort of ruler you need when the nearest large galaxies are your close neighbors. So the constant is saying this: for every megaparsec of distance you travel outward, galaxies recede about 70-something kilometers per second, faster than they did 1 megaparsec closer in. Sit with that for a moment, because it is the heartbeat of everything that follows. Take a galaxy 1 megaparsec away, and it drifts from us at roughly 73 or 74 kilometers each second. Take a galaxy 2 megaparsecs away, and it drifts at twice that. 10 megaparsecs, 10 times that. The recession piles up, step after step, the deeper you look. This steady, repeating relationship between distance and speed is the single cleanest evidence we have that we live inside a growing universe. And pinning down its precise value has been one of the great quests of modern astronomy for the better part of a century. And here is the first thing that should make you sit up, because it turns this from a dry measurement into something with real stakes. That single number does not just describe how fast the universe grows. Run it backward, and it tells you how long the universe has been growing at all. In other words, how old everything is. A faster expansion, all else being equal, implies a younger cosmos, because it took less time for galaxies to reach their present separations. A slower expansion implies an older one. So these two rival numbers are not only two speeds, they are quietly two different ages for the universe. The lower value, near 67, fits comfortably with a cosmos a little under 14 billion years old. Push the rate up toward the higher value, and you begin shaving time off the history of everything, on the order of 1 billion years, give or take. That may not sound like a catastrophe, but 1 billion years is not nothing. It is time enough for whole generations of stars to be born and die. When two ways of measuring the same universe cannot agree on how old it is, that is not a rounding error. That is a fracture running straight through the foundation. Which brings us to the man whose name is stamped on the whole affair, and to a common misunderstanding worth clearing away before it can do any damage. The title of this story says that Hubble just confirmed something. It would be easy to hear that and imagine an astronomer at an eyepiece last year, discovering cosmic expansion for the very first time. That is not what happened, and the truth is far more interesting. Cosmic expansion was worked out generations ago. In 1929, the American astronomer Edwin Hubble published measurements showing that the more distant a galaxy was, the faster it appeared to be flying away. The first solid observational sign that the universe was not static and eternal, but growing. And a couple of years before that, a quiet Belgian priest and physicist named Lemaitre had already derived much the same idea from theory, tracing the expansion backward in his mind toward a dense, fiery beginning. So the fact of expansion is old news, settled science, one of the bedrock discoveries of the 20th century. But settling that the universe expands was only the beginning of the fight. And the fight over how fast it expands turned out to be one of the longest and most bitter in the history of astronomy. Hubble's own first estimate of the constant was wildly too high, so high that when you ran it backward, it implied a universe younger than the rocks in the ground, younger even than the Earth itself, whose age geologists had already measured. That was an outright paradox. A cosmos supposedly younger than the planets inside it, and it hung over the field for years like an accusation. As the measurements slowly improved across the middle of the 20th century, the paradox eased, but the disagreement did not. Two great camps of astronomers formed, each armed with its own data and its own methods, and each convinced the other was wrong. One camp, led by the formidable observer Alan Sandage, championed a low value, an expansion rate down near 50 kilometers per second per megaparsec, implying an old and stately universe. A rival camp pushed for a value roughly twice as high, near 100, twice as high. For decades, the smartest people in the field could not agree on the pulse of the cosmos to within a factor of 2. And the argument grew personal enough that conferences turned frosty and the two sides could barely share a room. Notice what changed to break that stalemate, because it is the very thing that has now trapped us in a new one. What ended the old war was precision. As telescopes sharpened and methods multiplied, especially once the Hubble Space Telescope went to work on the problem in earnest, the enormous factor of 2 uncertainty began to collapse. The rival estimates, once spread from 50 to 100, were squeezed together until they converged, by the turn of the century, on a value in the low 70s. The great historic disagreement did not end because one camp finally crushed the other. It ended because the error bars shrank until there was no longer room for wild disagreement. And that is exactly why the modern tension is so much more menacing than the old one. In the old days, a gap between two numbers could always be blamed on sloppy measurement, because the measurements really were rough. Today the measurements are exquisite, the uncertainties tiny, and yet a gap remains. When imprecise numbers disagree, you shrug and sharpen your tools. When two ferociously precise numbers disagree and refuse to come together no matter how much sharper the tools become, you're looking at something that mere carelessness cannot explain. So when you see the name Hubble attached to this modern crisis, it points at two things at once. It points at the Hubble Space Telescope, the orbiting observatory that spent decades building the strongest local measurement of the expansion rate we have ever assembled. And that did more than any instrument to end the old factor of 2 war. And it points, through that instrument, at the whole modern effort to nail down the constant with a precision that the astronomers of 1929 could only have dreamed of. The word confirmed in the title does not mean anyone has proven which side is right, or discovered the hidden new physics that would explain the gap. It means something more unsettling and more honest. The disagreement itself has been checked, and rechecked, and hunted for flaws, and it keeps surviving. The tension has been confirmed to be real, not resolved. So let us make the two numbers concrete, because they are the two poles this entire story is stretched between. On one side stands the local measurement, the value you get when you roll up your sleeves and measure the nearby, mature universe directly, galaxy by galaxy, using stars and exploding suns as your yardsticks. That route lands, again and again, at about 73.5 kilometers per second per megaparsec. On the other side stands a very different kind of number. Not a direct measurement of today's sky at all, but a prediction. You take the faint afterglow of the young cosmos, the light released when the universe was only a few 100,000 years old. You feed it into our best mathematical model of how the universe evolves, and you run that model forward across billions of years to ask what the expansion rate ought to be today. That route lands near 67, closer to 67.4, and here is the knot at the heart of it all. Both of those numbers are the same quantity. Both are the Hubble constant, the present-day pulse of expansion. They are two answers to one question, and under our current, unmodified model of the universe, they cannot both be correct at the same time. The difference between 73.5 and 67.4 might look small, almost trivial, the kind of rounding error you would shrug off in ordinary life. It is not. In this arena, with the razor-fine precision both sides have now achieved, that gap is enormous. It is far too large to be dismissed as bad luck or statistical noise. It is a genuine, quantifiable contradiction sitting at the center of our description of the universe, and no one has been able to make it go away. You can already feel why this matters, even before we chase down the details. The expansion rate is not some isolated trivia bolted onto the side of cosmology. It is a master key. It helps set the age of the universe, how long there has been between the beginning and this exact moment. It threads through our accounting of what the universe is made of. How much ordinary matter, how much dark matter, how much of the mysterious dark energy driving expansion onward. It shapes our picture of how cosmic structure grew and where everything is ultimately headed. Two irreconcilable values for that one number is not a small bookkeeping slip. It is a hint that the story we tell connecting the universe's fiery infancy to the calm, star-filled sky above you tonight may be missing a page. For years, the reasonable, almost comforting response was to assume that one side had simply made a mistake somewhere. Measuring the cosmos is monstrously difficult work. Perhaps the local astronomers had a subtle flaw baked into their yardsticks. Perhaps the early universe modelers had leaned too hard on an assumption buried deep in their equations. Errors like that have unraveled plenty of astronomical puzzles before, and the smart money for a while was on exactly that outcome here. Someone would find the loose thread, give it a pull, and the two numbers would slide together with a satisfying click. Crisis over. Textbooks intact. That is not how it has played out. Every time the tools got sharper, the honest expectation was that the tension would ease. It kept doing the opposite. And that reversal, the fact that better data made the problem worse rather than better, is the engine that drives this entire story forward. To feel the full weight of it, you have to understand that the two numbers are not produced by pointing two telescopes at the same patch of sky and reading off different results. That would be a shallow disagreement, easy to blame on one instrument or the other. The reality is stranger and deeper. The two numbers come from two fundamentally different acts of knowing. The local number is a measurement. It is astronomers building a physical chain of distances outward through the nearby universe using objects whose true brightness they believe they understand, and watching how recession speed climbs with distance. It is hands-on, empirical, rooted in the here and now, the universe as it exists at this late, mature stage of its life, 13.8 billion years after the beginning. The early universe number is not a measurement of today at all. It is an inference. You observe the oldest light in existence, the cosmic microwave background, that faint uniform glow left over from when the infant universe first cooled enough to become transparent. You measure the delicate pattern of hot and cold ripples frozen into that glow with exquisite care. And then This is the crucial part. You assume that our standard model of cosmology is correct. The model astronomers call lambda CDM, and you use it to evolve that ancient snapshot forward across the whole history of the universe until it predicts what the expansion rate should be right now. The early universe value is only as trustworthy as the model doing the fast forwarding. It is a prediction about the present, extracted from the deep past through a chain of theory. Hold those two things apart in your mind, because keeping them separate is the key to understanding everything that comes next. On one side, a direct measurement of the nearby, grown-up universe. On the other, a prediction about today inferred from the universe's earliest light by assuming our model is right and running it forward. These are not the same telescope disagreeing with itself. They are two profoundly different roads to the same destination, and they are arriving at two different places. Now, if you wanted to attack this puzzle, the obvious first suspect is the local measurement, because it is a physical chain, and any chain can have a weak link. This is precisely where the Hubble Space Telescope earned its central role. Over many years, it did the painstaking work of building that local chain of distances, star by star, galaxy by galaxy, assembling the strongest direct case that the universe really is expanding at that higher rate near 73.5. The critics, doing exactly what good scientists should do, zeroed in on a specific vulnerability in that chain. A worry that one of its most important rungs, a particular kind of pulsing star used as a distance marker, might be systematically fooling us in the crowded, cluttered depths of faraway galaxies, making the whole local number an illusion. If that criticism were right, the tension might simply dissolve. The local number would sag down toward the early universe prediction. The two would meet in the middle, and cosmology could exhale. So the obvious move was to bring in a sharper eye and check. That sharper eye was the James Webb Space Telescope. Webb was not sent up to independently rebuild the entire distance chain from scratch, and it did not measure the early universe's prediction. That is a different route entirely. Webb was aimed at the single most doubted rung of the local ladder, with vision keen enough to test, once and for all, whether that suspected flaw was real. It was, in effect, sent to break the local measurement, to find the crack that would let everyone off the hook. And then, in 2026, the story took the turn that transformed a nagging discrepancy into a full-blown crisis. A sweeping international effort gathered up not just one type of distance marker, but a whole battery of independent methods, different kinds of stars, exploding suns, and other cosmic yardsticks that had each been developed and refined on their own, and it wove them together into a single, rigorous framework. The idea was elegant and pitiless. If the high local value were the product of one flawed technique, then leaning on many independent techniques at once should expose the flaw and pull the answer down. Instead, the methods converged. They agreed with one another, and they agreed stubbornly on a value right around 73.5, holding firm against the 67 the standard model demands from the early universe. And that stubbornness is the whole story in miniature. A single measurement can be wrong. That happens all the time. But a value that holds its ground while method after method is hurled against it is no longer the kind of thing a quiet correction is likely to sweep away. The local number had by now survived an escalating series of the toughest cross-examinations astronomers could devise including the one weapon everyone expected to break it, and it had not so much as flinched. The exits that once let scientists shrug and say a hidden error would eventually surface were, one by one, quietly swinging shut. And with each one that closes, the possibility on the other side of the door grows a little harder to ignore. That the two numbers disagree not because someone slipped, but because the universe changed between its beginning and its present, in a way our model does not yet capture. But we are getting ahead of ourselves, and the promise of this story is that we earn every step, honestly, closing off the easy answers before we reach for the hard ones. Because a fair question is already forming, and it is the right one to end on. All of this rests on the local measurement, on the claim that astronomers can walk out into the nearby universe and directly clock how fast it is growing, and arrive at 73.5 with real confidence. And that claim should stop you cold because it hides an impossibility. Think about what a direct distance measurement even means out there. You cannot stretch a tape measure to another galaxy. You cannot bounce a signal off a star tens of millions of light years away and wait the 100 million years for the echo. You cannot travel there. Every object in this story is unreachably far, forever beyond any probe we could build. The nearest large galaxies are millions of light years off. The exploding suns that anchor the far end of the local measurement lie hundreds of millions of light years deep. We are marooned on one small world, staring across a gulf we can never cross. And yet, astronomers claim to know those distances precisely enough to weigh the expansion of the entire cosmos against a rival prediction, and to find the prediction wanting. How is that even possible? How do you measure a distance you can never travel, to an object you can never touch, and trust the number enough to say the standard model of the universe might be wrong? The answer is one of the most ingenious pieces of reasoning in the history of science. A staircase of interlocking techniques, each one calibrating the next. Reaching rung by rung from our own backyard, out into the deep and expanding dark. Astronomers call it the cosmic distance ladder. And to understand why the Hubble tension has become so impossible to dismiss, you first have to climb it. Every measurement in astronomy that reaches beyond our own small neighborhood rests on a single, stubborn trick, and once you see it, you can never unsee it. You never measure the whole distance at once. You measure a distance you can genuinely reach, something close and checkable, and you use it to calibrate a tool that reaches a little farther. Then you use that tool, now trusted, to calibrate a second tool that reaches farther still. And you keep going, handing off the measurement from one method to the next, each one overlapping the one before it, until you have crept outward across gulfs no ruler could ever span. Astronomers call the whole apparatus the cosmic distance ladder, and the name is almost right, though a better picture might be a surveyor's chain of overlapping measuring tapes. Imagine trying to measure the length of a country with a handful of short tapes. No single tape reaches more than a few meters, but if you lay the first one down, mark where it ends, lay the second one as starting from that mark, and carry on, the small overlaps let you stitch together a distance thousands of times longer than any one tape. The magic and the danger lives entirely in those overlaps. Get one handoff wrong, misplace a single mark, and every distance beyond it inherits the error, quietly and invisibly, all the way out to the edge of the map. That is exactly how astronomers measure the expanding universe. And to understand why the higher value near 73.5 has become so hard to dismiss, and why one particular handoff was accused of poisoning the whole result. You have to walk up the ladder rung by rung, from the solid ground beneath our feet, out into the deep dark where galaxies flee. The first rung, the one everything else is built on, is the only one that requires no assumptions at all. It is pure geometry. The same geometry a surveyor uses on a fine afternoon, and it goes by the name parallax. You already carry the instrument for it in your own skull. Hold your thumb up at arm's length. Close one eye, and note where your thumb sits against the far wall. Now switch eyes without moving your thumb. Your thumb appears to jump sideways against the background. It did not move. You changed your viewpoint, and the shift in apparent position betrays the distance. Bring your thumb closer to your face, and the jump grows larger. Push it farther away, and the jump shrinks. Measure the size of that jump, and if you know how far apart your two eyes are, simple trigonometry hands you the distance to your thumb without your ever touching the wall. Astronomers play the same game on a colossal scale, and their two eyes are the two ends of Earth's orbit around the Sun. Look at a relatively nearby star in the depths of winter. Then look again 6 months later from the far side of our orbit, hundreds of millions of kilometers away, and the nearby star appears to shift ever so slightly against the vastly more distant stars behind it. That tiny shift, teased out with fanatical precision, gives the stars true distance through nothing more than the shape of a triangle. And when I say tiny, I mean almost absurdly so. Even for the closest stars, the shift is smaller than the width of a coin seen from across a city, an angle so minute that for centuries astronomers simply could not measure it at all. Which is why the ancients doubted the Earth moved. No guessing about how bright the star really is. No model of how the universe evolves. Just angles and a known baseline. It is the bedrock of the entire structure, the one measurement that cannot be argued away, because it leans on geometry and nothing else. In recent years, this rung has become almost unbelievably sharp. A dedicated European spacecraft spent years mapping the precise positions of well over 1 billion stars in our own galaxy, measuring their parallax shifts so finely that it fixed distances across the Milky Way, with a confidence earlier astronomers would have found miraculous. But parallax, for all its purity, has a hard limit. The farther a star sits, the smaller its 6-month shift becomes, until eventually the wobble is too faint to measure, and the method runs out of reach. Geometry alone carries you across our own galaxy and to its nearest companions. And then it stops. To go farther, you need a different kind of tool entirely. You need a light of known strength. This is the idea that makes the whole ladder possible, and it is worth pausing on, because everything above the first rung depends on it. Imagine you are standing in a vast dark field at night, and scattered across it are light bulbs. Suppose you know for certain that every one of those bulbs is manufactured to shine with exactly the same wattage, the same true brightness. A bulb close to you looks blazing and brilliant. A bulb far away looks faint and dim. Because you know their true output is identical, the apparent dimness tells you the distance directly. Light spreads out and thins as it travels, obeying a strict and unforgiving law. So a bulb that looks 4 times fainter must be twice as far away. Astronomers call such an object a standard candle, a source whose true luminosity you already know, so that its apparent faintness becomes a ruler. Find a standard candle in a distant galaxy, measure how dim it looks, and you have measured how far away that galaxy is. The whole problem, of course, is finding objects in the sky whose true brightness you can actually trust. Stars come in wild varieties, some feeble, some ferociously luminous, and you cannot tell the true output of a random point of light just by looking at it. But nature, it turns out, left us a gift, and the story of how we found it belongs to a woman working in near total obscurity at the dawn of the 20th century. Her name was Henrietta Leavitt, and in the early 1900s, she was employed at the Harvard College Observatory as one of a group of women hired to do the painstaking, underpaid work of measuring stars on photographic plates. While cataloguing a particular class of pulsing star, stars that swell and shrink and so brighten and dim in a steady rhythm, she noticed something that would crack the universe open. These stars, called Cepheid variables, did not pulse at random. The brighter a Cepheid truly was, the more slowly it pulsed. A dim one might complete its cycle of brightening and fading in a couple of days. A brilliant one took weeks, its rhythm long and stately. The timing of the pulse, which anyone with a clock and patience can measure, betrayed the star's true luminosity. Think of it like a set of bells. A tiny handbell rings with a high, quick, quiet chime. A great cathedral bell swings slowly and booms out across an entire city. If you learned that the pitch and pace of a bell reliably told you how loud it truly rang, then hearing a bell from far away and timing its slow, deep toll, you could know its true volume, and from how faint it sounded to you, work out how far away the tower stood. Leavitt had found the astronomical version of that law. Time a Cepheid's pulse, and you learn its true brightness. Compare that true brightness to how dim it looks in the sky, and you have its distance. There was one missing piece. Leavitt's law told you which Cepheids were brighter than others, but not the exact wattage, so to speak, of any single one. To convert a relationship into real distances, someone had to measure the true distance to at least a few Cepheids by an independent method, to set the 0 point of the scale. And this is where the ladder's overlaps do their quiet, essential work. The cleanest way to set that 0 point is to reach back down to the geometric rung and find Cepheids close enough to have their distances pinned by parallax alone within our own galaxy, so that pure geometry fixes the scale with no assumptions at all. But astronomers wanted more than one independent anchor, because a ladder resting on a single foot is a ladder waiting to fall, and so they built additional anchors rooted in geometry as well. One of the most beautiful of these sites in a satellite galaxy of the Milky Way called the Large Magellanic Cloud, and it deserves a moment because it shows how much cleverness hides inside a single rung. Scattered through that companion galaxy are pairs of stars locked in orbit around one another, oriented so that, from our vantage point, each star periodically passes in front of the other. Astronomers call them detached eclipsing binaries. As one star slides across its partner, the total light we receive dips, then recovers, then dips again as the partner passes back across, tracing a precise rhythm of eclipses. And buried in the details of that rhythm is a small miracle of physics. By timing how long each eclipse lasts, and measuring, from the light of the stars, how fast the two are moving in their orbit, astronomers can work out the true physical sizes of the stars. Knowing a star's true size and its temperature tells you its true luminosity, its actual output. And once you know the true output, and can see how faint it appears, you have a distance, derived almost entirely from geometry and basic stellar physics, with no standard candle assumed at all. This gives the ladder a second firm foot, independent of the first, standing in a galaxy just far enough away to calibrate the Cepheids that live there. Yet another anchor comes from a more distant galaxy, whose central region contains clouds of gas orbiting its black hole in a way that acts almost like a built-in geometric gauge, yielding a distance rooted in raw physics rather than assumption. Several anchors, several independent feet, all planted in geometry, all agreeing. But before the Cepheids can be trusted as a yardstick, there's a second great enemy of every standard candle to reckon with, and it is worth naming plainly, because it will return to haunt the whole story. That enemy is dust. The space between the stars is not perfectly empty, it is threaded with vast, thin clouds of fine grains, and starlight passing through them is dimmed, robbed of some of its brightness before it ever reaches us. This is deadly for a method built on judging distance from apparent brightness, because a Cepheid seen through a veil of dust looks fainter than it truly is, and fainter, by the iron logic of the standard candle, reads as farther away. Dust can make a galaxy seem more distant than it is, tilting the ladder just as surely as any error in the stars themselves. Worse, Cepheids live precisely in the dustiest neighborhoods, the young star-forming regions thick with the very clouds that dim them. Astronomers have a clever defense, though. Dust does not dim all colors equally, it scatters blue light more than red. So a dimmed star also looks reddened, its color subtly shifted. By measuring a Cepheid in several colors at once and watching how reddened it appears, astronomers can gauge how much dust lies in the way and correct for the dimming. And there is a deeper trick still. The longer, redder wavelengths of infrared light slip through dust far more easily than visible light does, so observing Cepheids in the infrared sidesteps much of the problem from the start. Hold on to that fact about infrared, because it is precisely the advantage a certain new telescope would later bring to bear on this exact rung. With those anchors nailing down the 0 point and the dust accounted for, the Cepheids were transformed from a curiosity into a yardstick. Now, whenever astronomers could spot Cepheids in some more distant galaxy, they could time the pulses, read off the true brightnesses, measure the apparent dimness, and calculate how far that galaxy lay. The second rung was in place. The measurement had climbed off the first tape and onto the second, reaching out to galaxies far beyond the range of parallax, tens of millions of light years into the surrounding cosmos. But even Cepheids, for all their power, cannot carry you far enough. They are individual stars, and stars, however luminous, fade into invisibility across truly cosmic distances. To measure the expansion of the universe, you cannot stay in the local neighborhood, because right around us the gentle gravitational pull of nearby galaxies muddles the clean signal of expansion. Galaxies here jostle one another, drifting this way and that, so their motions are a messy sum of cosmic expansion and local tugging. To read the pure expansion, the smooth outward flow that the Hubble constant describes, you have to go much deeper, out to distances so vast that expansion overwhelms all the local jostling and dominates completely. That deep, orderly regime has a name of its own, the Hubble flow, and no single star can be seen out there. So the ladder needs a third rung, a beacon far brighter than any star, bright enough to be seen across hundreds of millions, even billions, of light years. That beacon is one of the most violent events in nature, the detonation of an entire star. Specifically, a particular species of stellar explosion called a Type 1a supernova. These explosions are special for a reason that verges on the miraculous. A Type 1a supernova is thought to occur when a dense stellar ember, the burnt-out core left behind by a dead star, accumulates matter until it crosses a precise physical threshold and blows itself apart in a runaway thermonuclear blast. Because that threshold is nearly the same every time, set by the same unbending laws of physics, these supernovae tend to explode with very nearly the same true brightness. But here is the subtlety that makes them trustworthy. And it is more elegant than simple sameness. They are not perfectly identical, and astronomers do not pretend they are. What saves the method is that the explosions carry their own honesty inside them. A Type 1a supernova does not just flash and vanish. It brightens over days and then fades over weeks, and the exact shape of that rise and fall is linked to its true power. The intrinsically brighter explosions fade more slowly, lingering as they dim, while the fainter ones drop off more quickly. So by watching how fast a given supernova declines, astronomers can read off how luminous it truly was, and correct each one to a common standard. It is as if every flashbulb in the cosmos came stamped with a hidden label announcing its exact wattage, if only you were patient enough to watch it fade. Once corrected this way, they become very close to identical beacons, standardizable candles of staggering power, briefly outshining 100 billion ordinary stars, visible clear across the observable universe. But a flashbulb is only useful as a ruler if you know its true wattage, and here the ladder performs its most crucial handoff. In galaxies near enough to contain Cepheids, astronomers wait, sometimes for years, for a Type 1a supernova to erupt in that same galaxy. When one does, they have both tools in a single place. The Cepheids tell them the true distance to the galaxy. Knowing the distance and measuring how bright the supernova appeared, they can work backward to the supernova's true luminosity, calibrating that cosmic flashbulb against the star-based ladder below it. The Cepheids, in effect, teach the supernovae exactly how bright they really are. And it is worth pausing on just how slender this crucial handoff is, because it will matter enormously in a moment. For a galaxy to serve in this calibration, it must be a rare kind of coincidence, close enough that the Hubble Space Telescope could pick out its individual Cepheids, and also a galaxy that happened to host a Type 1a supernova we actually caught in the act. Galaxies meeting both conditions are not common. The entire modern calibration of these cosmic flashbulbs rests on only a few dozen such galaxies. A few dozen. That is the narrow waist of the whole hourglass. The pinch point where the star-based ladder hands its measurement to the supernovae. And because the sample is so small, any systematic problem lurking in those particular galaxies, anything that quietly biased the Cepheid brightnesses inside them, would not average away into harmlessness. It would tilt the entire distance scale of the universe. Hold on to that, because it is exactly where the attack would come. Once that lesson is learned, the supernovae take the measurement and hurl it into the deep. Because they are so blindingly luminous, Type 1a supernovae can be seen and measured far out in the smooth Hubble flow, hundreds of millions of light years away, where expansion reigns unchallenged. Out there, astronomers measure two things for each supernova: how far it is, from its apparent brightness compared to the true brightness the Cepheids taught it, and how fast its host galaxy is receding. And that second measurement, the recession speed, deserves a closer look. because it is the half of the problem that is almost embarrassingly clean compared with the tortuous business of distances. We met redshift back at the beginning, the stretching of light by expanding space. But how does an astronomer turn that idea into an actual number? A specific speed for a specific galaxy? The answer is a kind of cosmic barcode. Every chemical element, when it glows or absorbs light, does so only at a precise and fixed set of colours. Its own signature pattern of bright or dark lines ruled across the spectrum. Hydrogen has its pattern, calcium has another, oxygen another still, and these patterns are laws of nature, identical in a laboratory on Earth and in a galaxy 10 billion light-years away. Spread the light of a distant galaxy into a spectrum, and those same familiar patterns appear, but shifted. Every line slid bodily toward the red end by the same fractional amount, as though the entire barcode had been gently stretched. Because astronomers know exactly where each line should sit when the source is at rest, they can measure to great precision how far it has slid, and that shift translates cleanly and directly into how fast the galaxy is receding. There is no ladder here, no chain of calibrations, no crowding, no dust to defeat the reading. It is a direct measurement, one of the most dependable in all of astronomy. Redshift is effectively the easy half of the puzzle. The entire difficulty of measuring the expansion rate, all the painstaking rung-by-rung labor we have been climbing through, lies on the distant side of the ledger. The speed side very nearly takes care of itself. Put the two halves together then, and the payoff arrives. For each of many supernovae scattered across the deep sky, you have a distance and you have a recession speed, and you plot one against the other. The slope of that relationship, how much faster galaxies recede for each additional stretch of distance, is the Hubble constant itself. 3 rungs, each calibrating the next. Geometry anchors the Cepheids. The Cepheids anchor the supernovae, and the supernovae, married to their redshifts, measure the expansion of the universe. This entire soaring structure did not build itself. It was assembled, rung by painstaking rung, over decades of work, and in the modern era, much of that labor was carried out with the Hubble Space Telescope by a team whose long-running effort became known as the SHOES program, led by the astronomer Adam Rees, who had already shared in one of the great cosmological discoveries of his generation. Year after year, the team hunted Cepheids in the host galaxies of Type 1a supernovae, refined the anchors at the bottom of the ladder, wrestled down the dust, and tightened every joint in the chain. And year after year, as their precision improved and their error bars shrank, the ladder kept handing back the same troubling answer. The local universe, measured directly, is expanding at about 74 kilometers per second per megaparsec. Not the 67 the early universe predicts. Higher. Stubbornly, consistently higher. For a while, the hope remained that this was a story about mistakes waiting to be found, and the critics did the honourable thing. They went looking for the weakest link, and they believed they had found it, sitting right in the middle of the ladder, at the Cepheid rung, in exactly those few dozen precious calibrator galaxies. The worry was subtle, physical, and genuinely serious, and it deserves to be understood clearly, because the whole crisis pivots on it. Cepheid variables are young, luminous stars, and young, luminous stars do not live in quiet, empty corners of a galaxy. They cluster in the bright, busy, star-forming regions, jammed together with countless other stars, wreathed in gas and dust. When such a galaxy sits tens of millions of light-years away, Even a superb telescope struggles to isolate one Cepheid cleanly from its neighbors. In the image, the light of the star you care about can blend with the unresolved glow of other stars crowded right beside it. And that blending, that crowding, threatens the single most important thing the whole method depends on: an honest measurement of how bright the Cepheid truly appears. Picture trying to judge the brightness of one particular candle in a stadium packed shoulder to shoulder with thousands of other lit candles. From a distance, the flames merge into a general glow, and the candle you are watching seems brighter than it is because the light of its neighbors bleeds into your measurement. Now recall the iron logic of the standard candle. If a Cepheid looks brighter than it truly is, you will conclude it is closer than it truly is, because for a light of known strength, brighter means nearer. And if your Cepheids make their galaxies seem closer than they really are, then every distance up the ladder comes out too short. And if cosmic distances are systematically underestimated, the expansion rate you calculate from them comes out too high. In one clean stroke, unmodeled crowding could take the true lower expansion rate and inflate it, manufacturing a Hubble constant near 73 out of a universe that was really expanding closer to 67. If that were true, the Hubble tension would not be a crisis at all. It would be a subtle bookkeeping error, a systematic bias baked into one rung of the ladder, and the whole unsettling mismatch would dissolve the moment the crowding was properly accounted for. This was not a fringe complaint. Champions of a rival distance marker, a different class of star known as the tip of the red giant branch. Older stars that live in the calmer, less crowded outskirts of galaxies, and so are far less prone to blending, measured expansion rates that tended to land a little lower, closer to 69 or 70. To some, that gap between the Cepheid answer and the red giant answer looked like a smoking gun, evidence that the Cepheids really were being nudged upward by the clutter around them, and that the famous tension was at least partly a mirage born of stellar crowding. The Shoes team pushed back hard. They had, they argued, corrected for crowding all along, using the sharpest images Hubble could deliver and careful modelling of the surrounding light. Their answer, they insisted, already accounted for the blending. But here was the uncomfortable truth at the centre of the argument. Correcting for crowding is not the same as removing it. As long as the correction was a model, an estimate of how much extra light to subtract, a residual doubt would remain. Perhaps the correction was imperfect. Perhaps a stubborn sliver of unmodeled blending survived. Small in any one galaxy but building, across those few dozen calibrators, into a systematic tilt of the entire distance scale. And crucially, that doubt would be expected to grow with distance, because the farther away a galaxy sits, the more severe the crowding becomes, and the harder it is to separate one star from its neighbors. The deeper into the universe the ladder reached, the more room there was for the crowding demon to hide. So the argument reached a genuine impasse, and it was the kind of impasse that only better eyes could settle. Not a better theory, not a cleverer statistical trick applied to the same old images. What was needed was raw resolving power, an instrument that could march right up to those crowded, dusty, distant Cepheids and physically pull them apart from the swarm around them, seeing each pulsing star cleanly enough that no one could argue its brightness was contaminated by its neighbors. If such a telescope looked at the very same Cepheids the Shoes team had measured with Hubble in the very same galaxies, and found that the crowding had been corrupting the brightnesses all along, then the distances would shift, the local expansion rate would sag towards 67, and the tension would quietly deflate. The critics would be vindicated, the crisis would evaporate, and cosmology could sleep soundly again. And by the time this debate came to its head, such a telescope had, at last, arrived. An observatory built to see the infrared universe with a clarity nothing before it could match. Its great segmented mirror gathering light with enough precision to resolve individual stars in the crowded hearts of galaxies where Hubble saw only a merged glow. It was, in a very real sense, the perfect weapon aimed at the perfect target. A machine that could both pierce the dust with its infrared eyes and walk into the stadium of candles and separate one flame from the thousands around it. The question was no longer abstract. It had narrowed to a single, testable point. Take the most doubted rung of the most important ladder in cosmology, hand it to the sharpest eye ever flown, and ask it plainly. Were the crowded Cepheids lying? Everyone understood what was at stake. If the answer came back yes, the tension was an illusion and the story ended there. If it came back no, then the last easy escape route would slam shut, and cosmologists would be left staring at a discrepancy with nowhere left to hide it. The James Webb Space Telescope turned its mirror towards those distant, cluttered stars. And what it saw when it finally pulled them apart is where this story stops being a debate about telescopes and starts becoming a problem about the universe itself. When the James Webb Space Telescope finally turned its great golden mirror toward those crowded, distant, doubted stars, it was not being asked to discover anything new about the expansion of the universe. It was being asked to do something more like the work of a forensic examiner called into a trial after the fact, handed a piece of contested evidence and told, plainly, to look closer than anyone had ever looked before, and report whether the evidence held up. The Cepheids that the Hubble Space Telescope had measured over so many patient years were the witness whose testimony the whole local case depended on, and the accusation against that witness was specific, that in the packed, glowing hearts of faraway galaxies, its light had been contaminated, its brightness overstated, its testimony quietly corrupted by the swarm of other stars pressed up against it. Webb was built to settle exactly that kind of question, where Hubble, for all its brilliance, saw a merged and softened glow in the most crowded regions. Webb's sharper vision could march right up to those same stars and separate them, resolving individual Cepheids cleanly out of the crush around them. And crucially, Webb sees the universe in infrared light, the longer wavelengths that slip through obscuring dust far more easily than the visible light Hubble mostly gathered. As we saw at the Cepheid rung, dust is the second great enemy of a standard candle, and it is thickest precisely in the busy, star-forming zones where Cepheids live. So Webb brought two advantages at once to the doubted rung. It could pierce the dust that muddled the measurement, and it could pull apart the crowd that inflated it. If the crowding demon was real, if it had been secretly tilting the entire distance scale and manufacturing a false expansion rate, this was the instrument that would drag it into the light. The SHOES team, led again by Adam Rees, did the disciplined thing. They did not simply glance at a single galaxy with Webb and declare victory. They aimed Webb at the very same Cepheids they had already measured with Hubble in the very same galaxies, so that the two sets of measurements could be laid directly against one another, star by star. They pushed outward across the full span of distances that the original Hubble measurement had covered, reaching all the way to a galaxy catalogued as AGC 5468, sitting about 130 million light-years away, near the far edge of the Cepheid-bearing territory the ladder relied on. This mattered enormously, because the whole worry about crowding was that it should get worse with distance. The farther out you go, the more severe the blending, the more room for a hidden bias to grow. If the corruption were real, it would reveal itself most clearly out there, at the deep end, where the Cepheids are most crowded, and the correction is hardest to trust. And Webb looked, and pulled the stars apart and measured their brightnesses cleanly across that whole range. And the answer it returned was not the one the critics had hoped for. Webb's cleaner, dust-piercing measurements of those individual Cepheids agreed with what Hubble had reported all along. When the two telescopes' readings of the same stars were placed side by side, they tracked one another faithfully. The distances did not shift. The Cepheid brightnesses that Hubble had so carefully corrected for crowding turned out, under Webb's sharper eye, to have been essentially right. There was no hidden inflation lurking in the crush, no systematic tilt growing with distance, no quiet corruption of the testimony. The witness, cross-examined by the most powerful instrument ever flown, held to its account. As Rees put it, having now spanned the whole range that Hubble observed, the team could rule out a measurement error of that kind as the cause of the tension with very high confidence. It is worth dwelling on how the test was designed, because its cleverness is what makes the verdict so hard to wriggle out of. The power of the comparison came from measuring the same stars twice with two entirely different machines. Hubble reads the universe chiefly in visible light through a single smooth mirror. Webb reads it in infrared through a great segmented eye built on wholly different principles. If crowding had been the culprit, the two telescopes would have disagreed, and disagreed more sharply the farther out they looked, because the contamination that fools a visible light instrument in a crowded field is not the same as what an infrared instrument would see. Instead, star for star, galaxy for galaxy, all the way to the deep end of the range, the two machines returned the same distances. Two instruments with unrelated strengths and unrelated weaknesses, converging on the same answer, is precisely the signature of a real measurement rather than a shared mistake. The crowding hypothesis did not just fail to be confirmed, it predicted a growing gap that simply was not there. So it is worth being precise about what this did and did not prove, because the temptation to overstate it is strong, and the truth is sharper than the overstatement. Webb did not independently rebuild the entire distance ladder from the ground up. It didn't go measure the early universe, or rederive the expansion rate from scratch by some wholly separate route. What Webb did was narrower and, in its way, more decisive. It took the single most doubted rung of the local ladder, the Cepheid rung, and it tested whether that rung had been quietly failing. It had not. And so, one of the strongest, most concrete explanations for the whole tension, the idea that crowded Cepheids had been fooling Hubble into a falsely high number, was not merely weakened. It was, for that specific and important failure mode, closed off. The escape route that so many had counted on to make the crisis evaporate turned out to lead nowhere. Notice what this does to the shape of the problem. Before Webb, a comfortable observer could say, the local number is probably an artifact. A bias in one tricky measurement and better resolution will bring it down toward the early universe value. After Webb, that particular comfort was gone. The local measurement of about 74 kilometers per second per megaparsec had survived the exact test designed to break it. The two telescopes were not in conflict. That framing gets it exactly backward. Webb and Hubble agreed. And their agreement is precisely what makes the discrepancy so hard to dismiss, because it means the high local value cannot be waved away as a quirk of Hubble's eyesight. The eyesight was fine, but settling the fate of the Cepheids only sharpens the real question. And to feel the full force of it, we have to leave the local ladder entirely and cross over to the other side of the case, to a completely different way of knowing the universe. Because remember, the number the local measurement disagrees with, the value near 67, was never a direct measurement of the sky today at all. It comes from somewhere else entirely, from the oldest light in existence, and from a chain of reasoning that could hardly be more different from climbing a ladder of stars. That light is the cosmic microwave background, and it is, in the most literal sense, a photograph of the infant universe. In the beginning, the cosmos was so hot and dense that it was opaque, a blazing fog in which light could not travel freely, forever scattering off a churning sea of charged particles. Then, roughly 380,000 years after the beginning, the universe expanded and cooled enough for that fog to clear. Charged particles settled into neutral atoms, the sea became transparent, and the light that had been trapped was suddenly set free to stream across space. That ancient light has been traveling ever since, stretched by billions of years of cosmic expansion, from a fierce glow into a faint whisper of microwaves that now bathes the whole sky. Point a sensitive enough instrument in any direction, and you can still detect it. The afterglow of creation, the single most distant and most ancient thing we can observe. A snapshot of the universe as it was when it was less than 1,000th of its present age. A European spacecraft called Planck mapped that ancient glow across the entire sky with extraordinary care, charting the faint pattern of slightly hotter and slightly cooler patches frozen into it. Those patches are not random. They are the fossilized ripples of sound waves that rolled through the primordial fog before it cleared, and their sizes and spacings encode, with astonishing richness, the fundamental properties of the young universe, how much ordinary matter it held, how much dark matter, the geometry of space, the seeds from which galaxies would later grow. Reading that pattern is one of the great triumphs of modern cosmology, a way of weighing the entire infant universe from the imprint it left on its first light. And there is a detail hidden in those frozen ripples worth pausing on, because it becomes its own kind of measuring stick later in the story. Those sound waves rolling through the primordial fog all began at the same instant and travelled at nearly the same speed. So by the moment the fog cleared, they had all reached almost exactly the same distance outward from their starting points. That distance became a characteristic size stamped permanently into the pattern of the cosmos, a preferred spacing between patches, like a single ruler laid down once at the dawn of everything. Astronomers call it the sound horizon, and it matters here because the early universe prediction leans on knowing that rulers' true length. Get the physics of the young universe right, and you know exactly how long that ruler is. And that same primordial ruler, expanded and faded over billions of years, is still faintly imprinted in how galaxies cluster across the sky today, which means it offers yet another independent way to probe the expansion. A thread we will pick up again. But here is the part that everything turns on, the part that so many summaries get wrong. Planck did not measure how fast the universe is expanding today. It could not have. That ancient light shows us the universe as it was, not as it is. What astronomers actually do is far more subtle. They take that exquisite baby picture of the cosmos, and then they feed it into our best mathematical model of how the universe evolves, the model called lambda CDM. And they let the model carry the infant universe forward through its entire history, aging it across all 13.8 billion years. To ask what the expansion rate ought to be now, it is a piece of cosmic forensic age progression. You have a photograph of the child, and you have a theory of how children grow into adults, and you use the theory to predict what the adult must look like today. The number near 67.4 is the output of that prediction. It is not a reading of the present sky. It is what the present sky must be if the standard model is right and you run it forward from the beginning. That distinction is the whole game. So let us plant it firmly. The local value of about 73.5 is a measurement of the mature universe, taken directly here and now with stars and supernovae. The early universe value of about 67.4 is a prediction about the present, inferred from the universe's first light by assuming our model of cosmic evolution is correct and evolving that ancient snapshot forward. These are not two telescopes squabbling over the same photograph. They are two utterly different roads to the same quantity. One paved with direct observation of the nearby cosmos, the other paved with a theoretical journey across all of cosmic time. When people say the tension is a disagreement between the late universe and the early universe model prediction, this is exactly what they mean. It is not Hubble versus Webb. It is the universe we can touch versus the universe our theory says should have grown out of its own infancy. And both roads are, on their own terms, magnificent. The early universe prediction is not some sloppy back-of-the-envelope guess. It emerges from a model that fits the entire intricate pattern of the ancient light with breathtaking success. A model that has passed test after independent test, that correctly accounts for the abundance of the lightest chemical elements forged in the first minutes of creation, that predicts the large-scale scaffolding of galaxies we actually observe. The value near 67.4 carries a small, hard-won uncertainty and rests on some of the most scrutinized physics we have. That is precisely what makes the standoff so agonizing. This is not a case of one credible number against one shaky one. It is two precise, well-defended, internally consistent answers that simply refuse to be the same. Still, even after Webb's verdict on the Cepheids, a determined skeptic had one line of retreat left. Fine, they might say. The Cepheid rung is sound, but the local measurement is a ladder, a chain of handoffs, and Cepheids are only one link. Perhaps the flaw hides somewhere else in the chain, in the supernova calibration, in the anchors at the bottom, in some subtle assumption threaded through the whole structure. The tension had survived an attack on one rung, but the local number still leaned heavily on that single style of measurement. That one particular sequence of stars and explosions. Knock out any link, and the whole thing could still, in principle, come tumbling down towards 67. The answer to that last retreat arrived in the spring of 2026, and it changed the character of the debate. An international collaboration of astronomers set out to attack the problem from a completely different direction. Instead of trying to make one distance ladder ever more perfect, they asked a deeper question. What if you did not depend on any single ladder at all? What if you gather together every reliable, independent way of measuring cosmic distances that astronomers had painstakingly developed over the years? Methods that rely on entirely different kinds of objects and entirely different physics, and you wove them into one shared, rigorous framework. If the high local value were the artifact of one flawed technique, then leaning on many independent techniques at once should expose the outlier and drag the answer back down. But if all those separate methods, each with its own strengths and its own unrelated weaknesses, kept pointing to the same number, then the case for that number would become almost impossible to explain away as a fluke of any one approach. They called their framework the Local Distance Network, and the collaboration behind it, led by the astronomer Richard Anderson with Adam Rees among its members, published the result in the journal Astronomy and Astrophysics. It is important to understand what this network actually did, because it was not a matter of simply averaging a pile of published numbers together, which would be a crude and misleading thing to do. It was something more careful. Different distance methods share certain rungs at the bottom, the same geometric anchors, the same fundamental calibrations, and if you just average their final answers, you would secretly be counting those shared foundations several times over, and fooling yourself about how independent your methods really were. The network instead traced every method back to its roots, mapped out where they leaned on common ground and where they stood truly apart, and combined them in a way that honestly respected those connections, letting the genuinely independent pieces reinforce one another while refusing to double count what they shared. It was, in effect, an audit of the entire enterprise of cosmic distance measurement, built to squeeze out the maximum honest agreement without any hidden circular reasoning. Its power lay not in precision alone, but in redundancy, in the sheer number of unrelated roads it brought into a single map. Consider the roll call of methods it drew upon, because each one is a distinct and independent way of judging cosmic distance. There were the Cepheids, of course, the pulsing stars already vindicated by Webb, but alongside them stood the tip of the red giant branch, a method that uses old, cool stars in the calm outskirts of galaxies, far from the crowded regions, a technique whose very virtue is that it is nearly immune to the blending that had been feared at the Cepheids. There were the J-region asymptotic giant branch stars, another population of aging stars with their own reliable brightness signature. There were mirror variables, elderly pulsing stars that beat with a slow rhythm of their own. There were megamarsers, galaxies with clouds of gas orbiting their central black holes in a way that yields a distance rooted almost purely in geometry. There were surface brightness fluctuations, a clever technique that reads distance from the graininess of a galaxy's light. And there were the Type 1a supernovae, the brilliant standard beacons that carry the measurement out into the deep Hubble flow. The red giant method deserves a special word here, because it is the one that had, for years, given the skeptics their best hope. Recall that this technique, favoured by a rival camp, had tended to land a little lower than the Cepheids, nearer 69 or 70, and that some had seized on the gap as evidence the Cepheids were inflated. So its inclusion in the network was not a formality, it was a test in its own right. Here was an independent method, built on old stars in the uncrowded outskirts of galaxies, immune to the very crowding that had haunted the Cepheids, and it was being brought onto common footing with all the others, its calibration traced back and reconciled with the shared anchors at the ladder's foot. If the red giants truly pointed low, toward the early universe value, the network was exactly the place that disagreement would show itself and pull the combined answer down. But that is not what happened. When the red giant measurements were placed on the same rigorous footing as the rest, their pull toward the low end proved far weaker than the headline numbers had suggested. Whatever modest difference remained sat comfortably within the ordinary give and take of independent techniques, and it landed the red giants much closer to the Cepheids than to the 67 the early universe demands. The method that had been the skeptics' great hope did not rescue them. Even taken at its own word, it sat on the high side of the divide, well above the prediction, another voice in the chorus rather than a dissenter. And this points to something worth making explicit about the very bottom of the whole structure. Because a clever critic might now ask whether the trouble hides not in any one method, but in the shared foundation they all rest on. Those few geometric anchors at the base of the ladder. If the anchors themselves were wrong, the reasoning goes every method built above them would inherit the same error, and their agreement would be worthless. A chorus all singing the same wrong note because they were all handed the same wrong sheet of music. It is a fair worry, and the honest answer is that the anchors are not a single point of failure, but several independent ones. The parallax measurements within our own galaxy, the eclipsing binaries in the satellite galaxy, the gas clouds orbiting the black hole in the distant anchor galaxy. These rest on different physics and could fail in different ways, and yet they agree with one another about the scale of the nearby universe. For the local result to be an illusion born at the anchors, several unrelated geometric methods would all have to be wrong by the same amount in the same direction, which is a far harder thing to arrange than a single slipped measurement. The foundation, like the methods above it, has been cross-checked, and it has held. Think of what it means to bring all of these into agreement. These are not variations on a single measurement. They lean on different stars, different physics, different assumptions, and they fail when they fail in different and unrelated ways. It is one thing for a single witness to insist on an account. It is another thing entirely for a whole room full of independent witnesses who never spoke to one another and who have nothing in common except what they saw to give the same testimony down to the detail. When independent methods with unrelated weaknesses converge on the same value, the most natural explanation is not that they all happen to share one hidden flaw. It is that they are all seeing something real, and converge they did. When the local distance network fused these many independent routes into its shared framework, the number it returned was 73.5 kilometers per second per megaparsec, with an uncertainty of less than 1 part in 90, a precision of just over 1%, not 67, not a value drifting down toward the early universe prediction now that the single ladder dependence had been broken. 73.5, holding firm right where the Cepheid ladder had been pointing all along, now backed by a chorus of unrelated methods all singing the same note. The redundancy that was supposed to expose a flaw instead confirmed the result. The local universe, measured every which way, is expanding faster than the standard model, evolved forward from the ancient light, says it should be. So stand back now and survey where the case rests, because the ground has shifted decisively beneath it. On one side sits a direct measurement of the nearby universe, near 73.5, that has now survived 2 escalating trials. It survived Webb's cross-examination of its most doubted rung. the crowded Cepheids, which turned out to be honest, and it survived the far broader test of the local distance network, in which a whole battery of independent methods, deliberately chosen for their unrelated weaknesses, refused to pull the number down and instead locked it in place. On the other side sits the early universe prediction, near 67.4, output of a model that fits the infant universe's first light with extraordinary success and passes independent test after independent test of its own. Two precise numbers, two internally consistent, well-defended descriptions of the same cosmic quantity, and a gap between them beyond 5 standard deviations by the usual reckoning, so unlikely to be a statistical accident that chance can no longer be blamed. That phrase, 5 standard deviations, deserves to be unpacked, because it is the language scientists use to decide when something has crossed from suggestive into undeniable, and it is doing quiet but enormous work here. Every measurement carries a fuzziness, a range within which the true value is expected to wobble simply because no instrument is perfect. A standard deviation is the natural size of that wobble. If two numbers differ by 1 standard deviation, you shrug. That is ordinary scatter, the kind of near mischance produces all the time. 2 standard deviations, still unremarkable, but the odds of a gap appearing by pure luck fall away with brutal speed as the standard deviations pile up. By the time you reach a separation of 5 standard deviations, the probability that random chance alone produced it drops to roughly 1 in a few million. Physicists have long treated that 5 standard deviation mark as the threshold for claiming a genuine discovery, the line beyond which a result is no longer plausibly a fluke of noisy data. The gap between the local measurement and the early universe prediction now sits beyond that line. In the cold grammar of statistics, this disagreement is not a coincidence waiting to resolve itself. It has passed the very same bar that physicists demand before they will announce that they have found something real. This is what it means to say the tension has been confirmed. Confirmed does not mean solved. No one has proven which value is correct. No one has caught the universe violating its own laws, or shown that the Big Bang picture is wrong, or demonstrated that some new force is at work. What has been confirmed is the durability and the credibility of the disagreement itself. The comfortable assumption that carried cosmology for years, that sharper tools would quietly close the gap, has been tested to its limit and has failed. Better data did not dissolve the tension, it hardened it. Each new instrument, each new method, each new cross-check was expected to be the one that made the problem go away, and each one instead made it more difficult to explain away. And so the escape routes are closing, one after another. And this is the momentum that carries us towards the deepest question of all. The idea that the local number came from a flawed measurement of pulsing stars, closed by Webb. The idea that it leaned too heavily on one fragile ladder, closed by the convergence of the local distance network. The idea that the rival red giant method would rescue the low value, closed when that method was brought onto common footing and stayed high. The idea that the whole thing was a statistical fluke, ruled out by the sheer weight of the discrepancy. One by one, the easy answers have been eliminated, and with each elimination, the space of remaining possibilities grows narrower and stranger. But narrower is not the same as empty, and honesty demands that we name what still stands. Ruling out crowding in the Cepheids is not the same as ruling out every conceivable systematic error, everywhere, in both of these staggeringly difficult measurements. Some subtle, shared, still unimagined flaw could yet be hiding on one side of the divide or the other, waiting for a future instrument to expose it. That door is not shut. But if it is not a hidden error, if both of these careful, cross-checked, independently supported numbers are telling the truth, then only one possibility remains. And it is the one that keeps cosmologists awake. It would mean the disagreement is not in our measurements at all. It would mean the story we tell connecting the universe's first light to the sky above us tonight, the model that ages the infant cosmos forward into the present, is missing something. Some ingredient we have not accounted for. Some chapter of cosmic history our equations do not yet contain. What could that missing ingredient be? What kind of thing could sit quietly inside the universe's evolution, invisible to our best model, and yet be powerful enough to pry two of the most carefully measured numbers in all of science apart and hold them there? That is the question the whole story has been climbing toward. And the candidates that cosmologists are now forced to consider reach into the deepest and most speculative corners of physics, into the nature of the dark energy driving the cosmos apart, into hidden particles, into the possibility that gravity itself does not behave quite the way we think across the vastness of time. And so we turn to the deepest question of all, the missing connection between the early universe and the universe we live in now. There is a peculiar kind of dread that belongs only to science, and it does not come from ignorance. It comes from the opposite. It comes from knowing two things extremely well, checking each of them until your confidence is almost total, and then discovering that the two things cannot both be true. That is where cosmology now stands. On one side, a measurement of how fast the nearby universe is expanding, near 73.5 kilometers per second per megaparsec. Tested and pressured and confirmed by a course of independent methods until it will not move. On the other, a prediction of that same rate, near 67.4, drawn from the universe's oldest light and carried forward by a model that has passed nearly every test we have ever set it. Both credible, both careful, both apparently right, and separated by a gap that refuses to close. Picture two great stone piers rising from opposite banks of a river, each one massive, each one anchored deep in solid rock, each one built by engineers who checked their work 100 times. The pier on the near bank is the local universe we can touch and measure. The pier on the far bank is the infant universe, read from its first light and aged forward by theory. For a bridge to stand, the two piers must meet in the middle, their spans reaching toward one another until they join. But when the standard model reaches across the river, its span arrives at the wrong height. The two ends do not line up. Something in the middle, somewhere across the billions of years that separate the early universe from the present, is missing. And without it, the bridge will not close. That missing span is the Hubble tension. And now, having eliminated the easy explanations one by one, we are left staring across the gap and asking what could possibly be strong enough to hold those two piers apart. Let us be scrupulously honest first, because honesty is the whole spirit of the thing, about the possibility we have not yet been able to slam shut. It remains conceivable that the answer is not new physics at all, but a subtle, still hidden flaw in one of the measurements, or in both. Ruling out crowding in the Cepheids, which Webb did so convincingly, is not the same as ruling out every conceivable systematic error, everywhere, across two of the most difficult measurements in all of astronomy. Perhaps a quiet, shared bias survives somewhere in the local distance work. in the calibration of the anchors, in some property of the supernovae we do not yet fully understand. Perhaps there is a small assumption buried deep in the reading of the ancient light, or in the model that ages it forward, that we have not thought to question. This possibility is not dead, and any cosmologist worth trusting will tell you so plainly. The history of the field is full of stubborn anomalies that turned out, in the end, to be someone's overlooked mistake rather than a crack in the cosmos. That door is not shut, and intellectual honesty requires that we keep our hand near it. But here is what makes this moment different from the ordinary run of anomalies, and why the mood among cosmologists has shifted from irritation towards something closer to awe. Every time the community expected the discrepancy to reveal itself as an error, and went looking for that error with the sharpest tools available, the error was not there. The measurement kept surviving. And a discrepancy that survives that much scrutiny begins to earn a different kind of respect. It stops looking like a bug in our instruments and starts looking like a message from the universe, one we have not yet learned to read. So let us take seriously the other branch of the fork, that both numbers are telling the truth, and that the fault lies not in our measurements, but in our story of how the universe grew. If that is so, then somewhere in the model that carries the infant cosmos forward into the present, an ingredient is missing, and the candidates cosmologists are now forced to weigh are among the strangest ideas in modern physics. Consider first the possibility that the trouble lies in the shadowy substance that dominates the universe's fate. Dark energy. The mysterious pressure that drives cosmic expansion, and, in recent cosmic history, has been accelerating it. In the standard model, dark energy is assumed to be perfectly steady, an unchanging property of empty space itself, and the same yesterday, today, and forever. That constancy is one of the model's core assumptions, and it is exactly the sort of assumption that, if wrong, could throw off the prediction. Suppose dark energy is not eternal and unchanging, but evolving. Its strength drifting slowly over the long ages of cosmic time. Then, the model that ages the early universe forward, assuming a constant dark energy, would carry that assumption like a hidden error. And the expansion rate it predicts for today could come out wrong. Tantalizingly, some recent large surveys of how cosmic structure has grown have produced faint hints, not proof, not confirmation, but hints that dark energy might not be quite as constant as the standard picture demands. Those hints are contested and preliminary, and no honest account would lean on them too hard. But they are enough to keep the idea of an evolving dark energy squarely on the table as one possible piece of the missing span. A second candidate reaches even further back, into the universe's first fractions of a second, and it carries the evocative name early dark energy. The idea is that for a brief window in the infant cosmos, before the ancient light was released, there existed an extra push, a fleeting burst of a dark energy-like influence that flared up and then faded away. Such a burst, if it were real, would subtly change the physics of that early era in a way that alters how astronomers should interpret the pattern in the first light. Recall that primordial ruler stamped into the ancient glow, the characteristic distance those early sound waves travelled before the fog cleared. A burst of early dark energy would have hurried the young universe along and shortened that ruler. And if the ruler is shorter than the standard model assumes, then the whole prediction drawn from the first light shifts, nudging the predicted expansion rate up from 67 toward the 73 the local universe insists upon. Early dark energy is one of the most actively studied proposals for closing the gap, precisely because it targets the early universe, where the prediction is born rather than demanding that the local measurement be wrong. But it is not a free lunch. Adding such an ingredient tends to disturb other things the standard model gets right, and it introduces new questions of its own. What was this fleeting influence? Why did it switch on when it did? And why did it vanish? A patch that fixes one problem while straining several others is not yet a solution. It is a candidate under interrogation. A third possibility does not touch dark energy at all, but asks instead whether the early universe held more kinds of things than we have accounted for. In the first moments of creation, alongside the familiar particles, there may have been additional unseen species streaming through the cosmos, a form of what physicists sometimes call dark radiation, extra relativistic ingredients not included in the standard recipe. More of these fast-moving species in the young universe would have changed the rate at which it expanded and cooled, and would in turn shift the interpretation of the ancient light and the prediction drawn from it. This is a way of adjusting the far pier of the bridge, the early universe, by enriching its contents. Like the others, it is constrained by a great deal of independent evidence, and it cannot be added carelessly. But it remains a live avenue, another possible strand of the missing span. And then there is the most radical possibility of all, the one that troubles the deepest foundation. What if the problem is not the contents of the universe, but the rules themselves? What if gravity, the force that governs how all of this expansion unfolds across cosmic time, does not behave over the vastest scales quite the way our theory assumes? Our understanding of gravity has been tested exquisitely within the solar system and in many other arenas, and it has passed magnificently. But the Hubble tension plays out across the entire span of the observable universe and the entire history of cosmic time, a regime far beyond anywhere we can run a controlled test. If the law of gravity was subtly different out there, in the deep reaches where the cosmos is stretched thinnest, then the whole machinery that carries the early universe forward to a prediction could be quietly miscalibrated. Modifying gravity is the boldest of the proposals, because it reaches for the bedrock, and for exactly that reason, it is held to the fiercest scrutiny. It is not favoured, but it cannot be dismissed, and that it must even be entertained tells you how serious the standoff has become. Notice something about this whole roster of candidates: evolving dark energy, early dark energy, extra hidden species in the young cosmos, a different behavior of gravity across cosmic time. Not one of them is confirmed. Not one of them has been shown to be the answer. Each one solves the tension only at a cost, straining against other measurements, raising new questions as fast as it settles old ones. This is the honest state of the field, a discrepancy robust enough that it can no longer be casually dismissed, and a set of proposed explanations, none of which has yet earned the right to be called the truth. We know the bridge has a missing span. We do not yet know what the span is made of. And anyone who tells you otherwise, who tells you that the mystery is solved, that new physics has been discovered, that the standard model has collapsed, is running well ahead of the evidence. The tension is confirmed. The cause is not. So how will we ever know? This is not a question destined to hang unanswered forever, and that is perhaps the most hopeful part of the whole story. Because the same relentless improvement in our instruments that hardened the tension is now being turned toward resolving it. And a wave of new eyes is arriving that will test the two piers of the bridge in ways never before possible. The most immediate of these is a new space telescope that carries the name of a pioneering astronomer, the Nancy Grace Roman Space Telescope, which may launch as early as the autumn of the very year this story is being told. Roman is built for breadth. Where earlier telescopes peered at the sky through a narrow keyhole, Roman will survey vast swaths of it at once with the same sharp precision, gathering enormous numbers of the very objects the distance ladder depends on, the pulsing stars and the exploding suns, across far more of the cosmos than has ever been charted this carefully. More objects means a firmer ladder, tighter calibration, smaller uncertainties, and a sharper test of whether the local number truly holds at 73.5 or has some slack in it we have not yet found. It is the next great step in measuring the near pier of the bridge. Alongside it works another mission, a European telescope called Euclid, designed to map the architecture of the cosmos across immense distances, charting how galaxies are arranged and how that arrangement has changed as the universe expanded. Euclid attacks the problem from the direction of cosmic structure, and here that primordial ruler returns one last time, because the faint imprint of those ancient sound waves is still there in how galaxies cluster across the sky. A standard length laid down at the dawn of everything and stretched ever since. By measuring the imprint at many different distances, Euclid can trace the expansion history along a route that leans on neither the distance ladder nor the reading of the first light in quite the same way as before, offering an independent handle on the expansion and on the behavior of dark energy itself, the very ingredient that some of the leading explanations propose to modify. If dark energy is evolving, if it is not the changeless constant the standard model assumes, this is one of the efforts most likely to catch it in the act. But the most beautiful of the coming tests do not lean on the distance ladder at all, and their promise is that they might sidestep the entire argument that has consumed this story. Consider the technique astronomers call standard sirens, when two extraordinarily dense stellar remnants spiral together and merge in the deep universe. They shake the very fabric of space, sending out ripples, gravitational waves that we can now detect directly. And the physics of those ripples is so clean that the strength of the signal reveals, all on its own, how far away the merger occurred, with no ladder, no Cepheids, no supernovae, no chain of calibrations to be accused of hidden bias. A gravitational wave carries its own distance written into its shape. Pair that geometric distance with the redshift of the merger's host galaxy, and you have measured the expansion rate by a route entirely independent of everything we have discussed, immune to the crowding worries and the calibration worries that have dominated the debate. Each such event is a fresh, unrelated witness. Gather enough of them, and they could confirm the high local value from a wholly new direction, or reveal something no one expected. There is yet another independent road, one that turns the warping of space itself into a ruler. When the light from a distant exploding star passes close to a massive galaxy on its way to us, the galaxy's gravity bends and splits that light into multiple images. And because the split light travels along paths of different lengths, the flashes of the explosion arrive in our telescopes at slightly different times, sometimes days or weeks apart. The precise pattern of those delays encodes the expansion rate. Through a chain of reasoning that depends on gravity and geometry, rather than on standard candles. Lensed supernovae are rare and difficult, but the coming surveys will catch many more of them, and each one offers another independent line on the number at the heart of the dispute. The same trick works with the brilliant flickering cores of distant galaxies whose light is bent into multiple images, their natural variations arriving along each path at different times, and astronomers are already assembling those delays into yet another ladder-free estimate of the expansion. Every one of these is a separate road toward the same crossing, and the more of them that arrive at 73.5, the harder it becomes to blame any single wrong turn. It is worth being clear about why these ladder-free methods carry such special weight, because they are, in the end, the true tiebreakers in this whole affair. Think back over everything the local measurement has weathered. The crowding of the Cephids, tested by Webb and cleared. The reliance on one style of star, broken open by the many methods of the local distance network. The worry about the shared geometric anchors, answered by their independence from one another. Each of those was a defense of the distance ladder, a demonstration that this rung or that foundation had not failed. But a determined skeptic could always, in principle, imagine one last hidden flaw threaded through the entire ladder at once, some subtle bias in the very idea of standard candles that every rung quietly inherited. Standard sirens and lensing time delays are the answer to that final doubt, because they do not climb the ladder at all. A gravitational wave does not care how bright a Cepheid is. It reads its distance straight from the physics of warped space. A lensing time delay does not lean on any exploding star's true wattage. It reads the expansion from the geometry of bent light and the clock of arriving flashes. These methods share none of the ladder's assumptions, none of its calibrations, none of its potential failure points, and that is precisely what makes them decisive. If some deep, shared error were secretly inflating the whole distance ladder towards 73.5, then these wholly separate routes, built on entirely different physics, would have no reason to agree with it. They would land somewhere else, and the high value would finally be exposed as an artifact. But if they too come in near 73.5, arriving at the same answer by roads that never touched a single Cepheid or supernova, then the last conceivable escape route closes, and the local number stands not as the verdict of one clever but fallible ladder, but as the convergent testimony of utterly unrelated ways of weighing the cosmos. That is the test the near future is racing to run, and it is why cosmologists watch every new gravitational wave merger and every newly caught cosmic mirage with such sharpened attention. The tiebreaker is being assembled, event by event, in real time. Here, then, is the shape of the near future. Multiple new instruments, multiple independent techniques, some sharpening the ladder we already have, some bypassing it entirely, all converging on the same question from unrelated directions. If they cluster around 73.5, the case for genuinely new physics will grow overwhelming, and the search for the missing span will intensify into the central quest of cosmology. If instead the newer, ladder-free methods begin to pull the number down or scatter, then the possibility of a hidden systematic error will come roaring back, and the story will take a turn no one can yet predict. Either way, this is not a mystery we are helpless before. It is a mystery we are actively closing in on, and the answer, one way or another, is likely to arrive within our lifetimes. And now, at the end, we can ask the question that has been waiting underneath this entire story. The question that lifts it above a mere quarrel about a number. Why does any of this matter? Why should it trouble anyone that two ways of clocking the expansion of the universe disagree by a handful of kilometers per second? The answer is that this single number is not a detail. It's a keystone. The expansion rate is woven into almost everything we claim to know about the cosmos as a whole. It helps set the age of the universe, the span of time between the beginning and this very moment. It threads through our accounting of what the universe is made of, the balance of ordinary matter and dark energy. It shapes our understanding of how the great structures of galaxies assembled, and it points toward the ultimate fate of everything, whether the cosmos expands gently forever or accelerates towards some colder, emptier end. To hold two irreconcilable values for that one number is not to misplace a decimal. It is to admit that the master narrative connecting the universe's fiery birth to the mature cosmos we inhabit right now has a gap in it that we cannot yet fill. Sit with the strangeness of that, because it is genuinely profound. The trouble is not that we know too little. In one sense, the trouble is that we know too much. If our measurement of the nearby universe was sloppy, we could shrug and blame the tools. If our model of the early universe was shaky, we could shrug and blame the theory. But that is not the situation we are in. The near peer is solid. The far peer is solid. Each description, taken entirely on its own, is a triumph, internally consistent, independently corroborated, hard-won, and credible. The infant universe, read from its first light, makes perfect sense on its own terms. The mature universe, measured with stars and supernovae, makes perfect sense on its own terms. It is only when you try to connect them, only when you insist that the child and the adult be the same cosmos governed by one unbroken set of rules, that the contradiction erupts. Two coherent stories that will not join into one. That is a stranger and more unsettling thing than simple ignorance. It suggests that our picture of the universe is not so much wrong as incomplete, missing a chapter somewhere in the long passage from then to now. There is a discipline in this that is worth honoring, and it runs against the grain of how we usually crave our mysteries resolved. It would be easy, and it would be false, to end by declaring that cosmology has been shattered, that the Big Bang is overthrown, that we have proof the universe is broken. None of that is true, and none of it is what the evidence says. The Big Bang framework remains one of the most successful theories in the history of science, explaining the ancient light, the abundance of the primordial elements, the grand architecture of galaxies. What the Hubble tension marks is not the collapse of that framework, but a crack in it. A place where the theory, for all its power, does not yet reach all the way across. Cracks are not catastrophes. In science, they are invitations. The great revolutions in our understanding have almost always begun exactly here, with a small, stubborn discrepancy that refused to go away, a number that would not behave, a tension that survived every attempt to explain it as a mistake. The precession of a planet's orbit that Newton's laws could not quite account for became the doorway to a new theory of gravity. The persistence of this tension may, in time, prove to be a doorway of the same kind. So let us set the two possibilities side by side, honestly, without flinching from either, because between them lies the whole meaning of this story. The first possibility is that an extraordinarily subtle error still hides somewhere in these measurements, an error so well concealed that it has survived Webb's challenge, survived the convergence of a dozen independent measurements, survived years of the most careful scrutiny that some of the finest minds in astronomy could bring to bear. If so, it is a systematic flaw of remarkable cunning, buried in one of the most checked calculations ever performed. And finding it will teach us something deep about the limits of our own instruments and our own assumptions. That would be humbling, and it would be valuable, and it is not impossible. The second possibility is the one that widens the eyes. It is that there is no error, that both numbers are true, that the nearby universe really is expanding faster than the standard model, evolved forward from the beginning, says it should be. And if that is the case, then the universe changed between its early state and its present one in some way our current theory does not describe. Some ingredient we have not named, some behavior of dark energy or gravity or the hidden contents of the young cosmos, is sitting quietly inside the history of everything, invisible to our best model, and yet powerful enough to hold those two mighty peers apart. It would mean that in the long, unwitnessed passage from the first light to this night, the universe did something we have not accounted for. It would mean the story is not finished being written. We do not yet know which of these it is, and that uncertainty is not a failure of this story, but its truest ending. What we know for certain is smaller and stranger and more honest than any tidy resolution. We know that two of the most carefully made measurements in all of science are pointing at the same universe and returning two different answers. We know that the disagreement has survived long enough and endured enough independent scrutiny that it can no longer be waved away as carelessness or coincidence. And we know that the bridge between the universe's beginning and the universe we live in tonight is missing a span, and that no one yet can tell you what that span is made of. Somewhere between the ancient afterglow of creation and the light falling on your eyes from the stars right now, the count does not balance. The early universe is one thing, the present universe is another. And the road that should connect them, the road our finest theory paves across 13.8 billion years, arrives at the wrong place. That is where this leaves us, standing on the near bank, looking across the dark water at the far pier, knowing both were built true and unable, for now, to explain why the span between them will not meet. The universe is not expanding wrong. The universe is expanding exactly as it pleases. It is our story of that expansion, the bridge we built in our minds between the first light and the last star, that is missing its middle. And somewhere out there, in the data still gathering, in the telescopes about to open their eyes, the missing piece is waiting to be found,